Hello and welcome to MyScience Tutorials. In today's video we are going to be looking at AC theory. This is actually a continuation of the first part of the AC theory, where we look at the root mean square current and then the root mean square voltage. Now in this second part we are going to be looking at phasor diagrams and then how we use the relationship we obtain from phasor diagrams to obtain valuable information to do calculations in an AC theory. So without wasting my time, let's get started. So what is a phasor diagram? Now a phasor diagram is just a vector diagram which is used to analyze an AC circuit. So any vector diagram at all that we use to analyze an AC circuit is referred to as a phasor diagram. Now there are three main components of an AC circuit. Okay, so first of all we can have a resistor. Okay, we can have an AC circuit with just a resistor inside. The symbol is given by this. Okay, this is a box, a rectangle, and then we have this representing the wires. Okay, so we can have a resistor or we have a capacitor, okay, which is actually used to store charges. Okay, now the resistor is, the unit is ohms. Okay, so we have this. Okay, now the capacitor is the unit is what? Farad or Faraday. Okay, and then the third component that we can have is what? An inductor. Okay, then inductor, we use this coil to represent an inductor, and then the unit is what? In Henry. Okay, so we are going to have a look at examples where we have what? Pure resistor just in the AC circuit, and then how we obtain the total resistance in that circuit. If we have capacitor, if we have inductor, how we obtain their various overall resistance when we make use of the phasor diagrams. So in the case of the resistor, now if we have a pure, the first type of circuit that we have is called what? The pure resistance circuit. Okay, now in the pure resistance circuit, what we have is we have our circuit. Okay, then we have our resistance. Okay, now across the resistance we have a voltage. We use VR to actually represent the voltage. Then we have the current flowing in this direction, and then this is the source of our AC. Okay, we use this curve to actually show this is an AC source. Okay, now in this circuit the current and then the voltage rise and fall together. Okay, so the first part of the AC theory we learned that AC, the voltage goes up and the current goes up and comes down in the form of a wave. Now the phasor diagram of this pure resistance circuit is we have a line straight, and then we have the current and then the voltage going in the same direction. This is the phasor diagram for a pure resistance circuit. So we have our IR, okay, moving in the same direction as our what? VR. So in this case this is a linear relationship. So to obtain the relationship between the voltage and then the current in this case, okay, it simply just follows the Ohm's law. Okay, which means we have our VR to be equal to what? I times what? R. Okay, this is IR. Okay, or simply just put voltage is equal to what? IR. So in this example, for us to calculate the overall resistance of this circuit, we just make R the subject. Okay, which R will be equal to what? Voltage divided by current. Now mind you, because we are dealing with an AC theory or an AC circuit, the voltage is not just any voltage. It is what? The root mean square voltage, and then the current is what? The root mean square current. So it means our resistance is equal to what? The root mean square voltage divided by what? The root mean square current. So this is how we use the phasor diagram. This is the phasor diagram for a pure resistance circuit. So this is how we use the phasor diagram to actually derive the relationship which we already know about a pure resistive circuit or a pure resistance circuit. Now let's have a look at the second type of circuit we have, which is the pure capacitor circuit. and see how that differs. Okay, so the second type of circuit is what we call the pure capacitor circuit. The pure capacitor circuit. Now, this is how it looks like. So we have our capacitor over here, and we have our AC source, our current moving in this direction, and then a voltage applied across the capacitor, which is represented by VC. Now, in this case, the current and then the voltage are said to be what? Out of phase. Okay, out of phase across the capacitor. Now let's take good note of this. Okay, the current and then the voltage are said to be what? Out of phase across the capacitor, which means what? The current leads the voltage by 90 degrees. So it means if this is our current, okay, the current is moving in this direction, it leads the voltage by an angle of what? 90. So it means the voltage is coming down an angle of 90, moving downwards in this case. So this is what the voltage will be, which is the VC, to mean the voltage across the capacitor, and then this is our current, which is, let me use I, okay, in this example. Sorry about that background noise. Okay, so this is how the Phasor diagram, okay, the Phasor diagram of what a pure capacitor circuit looks like. Now, for us to obtain the entire, or the resistance or the opposition offered to the flow of current through this circuit, okay, now remember the first example we used what? The resistance was R. Now in case of the capacitor, we don't use R, we use a special type of R. We use an X, and then we use C at the bottom. So this means what? Capacitive reactance. Okay, so this means capacitive reactance. That is the total opposition offered to the flow of current by the capacitor we have over here. Now the opposition of the flow of current in a resistive circuit is called resistance. That is for the first example. Now XC, what we have over here, is called what? Capacitive reactance, like I said earlier on. Okay, and is the measure of the opposition of a capacitor to an AC. Now from this we realize that the Phasor diagram, the current is leading the voltage by an angle of 90 degrees. So from here, okay, if you want to find the overall resistance offered by this capacitor, which is the capacitive reactance, it is given to us by what? 1 over what? 2 pi FC. So the capacitive reactance is what? 1 over 2 pi FC, where the C is what? The capacitance of the capacitor. Sorry about all the background noises. So the C over here is what we call the capacitance of the what? Of the capacitor. So the C is the capacitance of the capacitor, and that is what you will be given, and then it will be given in Faraday. So maybe you are given 20 farad. Okay, so in case you are given 20 farad, all you have to do is what? Input the 20 farad over here. You also be given a frequency, and then you use that together with the 2 pi, and then find the inverse of that to get your capacitive reactance, which is the total opposition offered to the AC by the capacitor in this particular circuit. Now let's have a look at the last type of circuit that we have in this AC theory, and then we look at some few examples on how to solve questions based on these theories. Now the last type, which is the third one that we have, is called what? Pure inductive circuit. Pure inductive circuit. Now the pure inductive circuit, like the other ones, it also, we have the inductor over here, okay, then we have our current flowing here, then we have our AC source over here, then we have a voltage across the inductor. Now in pure inductive circuit, the applied potential difference leads the current by what, 90 degrees. Okay, so in this case, okay, the Phasor diagram, okay, for an inductive circuit, we have the voltage leading the current. Okay, now in the other example, the capacitive reactance, we saw the current was leading the voltage by what, 90 degrees. But then in the Phasor diagram for an inductor or inductive circuit, we have the voltage rather, okay, the IV leading the current by 90 degrees. So we have the current over here, and then we have the voltage. So the voltage is now leading the current by what, an angle of what, 90 degrees. So this is the Phasor diagram of what, a pure inductive circuit. Okay, so the overall resistance in this case is what, XL. So this means what, capacitive inductive reactance. Okay, so the inductive reactance is, in this example, is given to us by what, 2 pi FL. Okay, where L is what, the inductance. Okay, the inductance of the what, the inductor that we have over here. So this summarizes the types of circuits that we have, and then how we find their total opposition to the flow of current. So in the case of an inductor, we have 2 pi FL. In the case of a capacitor, we have what, 1 over what, 2 pi FC. And then in the case of a pure resistor, we have the resistor to be what, voltage divided by current. So now let's have a look at some few examples to actually know how to use this formula in solving questions. So let's have a look at example number 1. So example number 1, we have here a 50 microfarad capacitor is connected to an AC source of 240 volts and then 50 hertz. What is the capacitive reactance and the current flowing through the circuit? Okay, so let's see how we can solve this. So the question is given us, we have a 50 microfarad capacitor. So we have the capacitance of the capacitor, okay, is what, 50 microfarad, which is what, 50 times 10 raised to the power minus 6 farad, or Faraday, someone will say. Okay. So we are given what, the voltage, which is the root mean square voltage. In this case is what, 240 volts, and then we are given frequency to be what, 50 hertz. Okay, so what do we need to do? We are asked to find what, the capacitive reactance, which is what, XC, and this is given to us by the formula 1 over what, 2 pi FC. So once we know this is the formula, we just substitute. So we have 1 divided by 2 pi, then the frequency over here is 50, multiplied by the capacitance, which is what, 550 times 10 raised to the power minus 6. Okay, so if we input everything over here into the calculator, we are going to get 63.7 ohms. Okay, so this is the value of our what, capacitive reactance in this particular example. Now the second aspect of the question is telling us to find the current flowing through the circuit. Now the current flowing through the circuit, just we use what, the Ohm's law. Okay, but then a modified version of the Ohm's law. We know the Ohm's law is what, V is equal to IR. Okay, that is, this is for what, a pure resistive circuit. Sorry, because this circuit is what, is an it's a capacitive circuit, our voltage will be equal to what, current multiplied by what, the capacitive reactance, which is what, XC over here. Okay, so this is the modified version of the Ohm's law that I was talking to you about. So this just simply means the resistance, but then it is the resistance of what, a capacitor, not that of a resistor. So in this case, if you want to find the current over here, we already know the voltage, which is the root mean square voltage over here. So we have 240 is equal to, we don't know the current, so we have I over there, which is the root mean square current, and then the opposition of it, which is the capacitive reactance, is what, 63.7. okay, this is I times. Okay, so we just divide by, our current will be what, 240 divided by 63.7. okay, so we get our current to be what, 3.77 amperes. So this is how we solve a question on a capacitive circuit in case we are given. Okay, so let's have a look at a second example. Okay, so that is the first one. So yeah, example number 2. So in the second example, we have here an inductor of what 2 Henry and negligible resistance is connected to a 12-volt main supply. If the frequency is 50 Hz, find the average current flowing through the circuit. Okay, so let's write solution. Now let's read the question again. Now an inductor of inductance, okay, 2 Henry. So we have our L to be what 2H, and then the negligible resistance, that means in case we have another resistor in this circuit, okay, the resistance is negligible, so we can ignore that. Okay, it's connected to a voltage of what 12 volts. So our root mean square voltage is what 12 volts. Okay, now if the frequency is 50 Hz, so our frequency is 50 Hz, find the average what current, which is what the root mean square current flowing through the circuit. So we have to find the root mean square current. This is what we don't know. And then straight from Ohm's law, we know in this example our root mean square voltage will be equal to what our current, which is what the root mean square current, times the inductive reactance, which is what XL, because we are dealing with a circuit containing an inductor. Okay, but now we need to find the inductive reactances. We don't know that. And then we know the inductive reactance is given by the formula 2 pi FL. So straight away we put our 2 pi here. The frequency is 50 times our inductance, the L, which is 2 over here. So we have what? If we input this into the calculator, we are going to get 628.3 ohms. Okay, so this is our inductive reactance. From there, we can just substitute our inductive reactance in place of this, and we get our current. So our current will be equal to what our voltage, which is what 12 volts over here, divided by our inductive reactance, which is what 628.3. So our root mean square current, okay, in this example will be equal to what 12 divided by 628.3. This will give us 0.019 amperes. So this does it for the second question. Let's have a look at one final question, and then we end this tutorial. Okay, so example number 3, we are asked to find what the question is telling us a 300 watt millihenry of an inductor of negligible resistance is connected to a 120 volt 60 Hz supply. Calculate the angular velocity, the inductive reactance, and then the current in the inductor. So this is simply just like the second example that we solved earlier. So if you like, you can pause the video and then go ahead and solve this, and then if you are done, you play the video and then we all look at it together. So go on ahead and pause the video. Alright, so I'm sure you are done with the video, you are done with the calculation, sorry. So let's have a look at what I have over here, and we compare and see whether our answer is correct. So first of all, we have our inductance, which is 30 times 10 raised to the power minus 3 Henry. That does it for the milli. Then we have our voltage, which is the root mean square voltage, is equal to what 120 volts. Our frequency is 60 Hz over here. So the I is telling us to find what the angular velocity, and then angular velocity is given to us by the formula 2 pi f. Okay, so this means we have what 2 pi times the frequency, which is 60. Okay, so this will give us what 377 radians per second. So this is the unit for angular velocity. So that's it for the first part of the question. Now the second part of the question is telling us to find the inductive reactance, which is what XL, and this is what 2 pi FL. Now can you see that we have the 2 pi f already over here? Okay, so we can say this is equal as what? Angular velocity L, which is equal to what? 377, which is the angular velocity, the 2 pi f that we've already calculated, times the inductance, which is 30 times 10 raised to the power minus 3 over here. And so if we input this into the calculator, we are going to get 11.31 ohms as our what? Inductive reactance. So now that we have our inductive reactance, we know what? Voltage, which is the root mean square voltage, is equal to the root mean square current times our inductive reactance. So it means our current will be equal to what? The voltage, which is 120 volts, divided by 11.31, and then this will give us what? 10.6 amperes. Okay, so this is how we solve questions based on the different types of circuit we have in an AC theory, whether it's a capacitor or an inductor or a pure resistor. Okay, in this example, in this video, we did not look at the calculation based on the pure resistance, because we have been doing that a lot. That is just from Ohm's law. So we look at how we solve the question when we have a pure capacitor, and then 2 examples when we have an inductor. So thank you so much for watching, and then the third part of this tutorial is also coming very soon, and in that part we'll be looking at if a combination of 2 or more components that we saw over here. So we'll be having a resistor and then a capacitor in series, how we get the total resistance. If we have an inductor and then a resistance and a resistor, sorry, how we look at the total resistance. And then if we have 3 of these components all together in one circuit, how we can calculate the overall resistance and get our current and then our voltage if the question asks us. So thank you so much for watching, and then I'll see you in the third and then the final part of this AC theory video. Thank you so much, and then I'll see you. Bye bye.